Hi there, I'm Dr. Ben Britton, and this is section 1 of the Introduction to EBSD lectures. In this section, we're going to look at some examples that will motivate you for the benefits and opportunities afforded by this microscopy technique. So why might we want to use the technique? Well, EBSD fundamentally enables us to scan microstructures. We can use that to create quantitative maps that enable us, for instance, to evaluate the grain size, grain shape, distribution of phases, and fundamentally map the grain orientations in the object. These can be influenced through processing, so for instance, if we change the strain path in deformation, that can change the shape and size of grains as well as their orientations. Furthermore, if we do heating or cooling, we can precipitate or change phases, we can get grain growth in a whole range of bits and pieces. The microstructure is critically important. This can influence the properties of the material, and things like the strength of the material could be anisotropic depending on the orientation of crystals. This could influence the ductility, the toughness, the hardness, the stiffness, the resistivity. We can add a whole range of different properties that are important. So an initial idea is in microstructural assessment. We could take a map, this is of some interstitial-free steel, and so this is a map of the ferrite grains that have been outlined in black grain boundaries that are shown here. So we can see the grains, we can see the orientations as encoded by little sort of cubes showing their orientations in this map down here, and it's encoded formally in the inverse pole figure coloring. So that's what we'll talk about a bit later, but the colouring which tells you about the orientations with respect to the x-axis, the y-axis and the z-axis. Broadly, we can see that the orientations are that there are a commonality of grains with the 1-1-1 orientation pointing out of the page. And that's common as found in sort of sheet steels, for instance, in this example. We can evaluate, this is a welded microstructure, and this welded microstructure, you've got the welding bead, you've got effectively the cooling of material from the edge of the weld inwards towards, and we can evaluate, for instance, the texture of these different grains as well as the grain shape and size as a function of the processing conditions in this laser weld. We can map across large samples, and so this is a tungsten carbide hard metal, and this is showing the tungsten carbide phase. By evaluating effectively the number of points indexed to the same orientation, we can construct a map of the grains in the material that then enables us to quantify the grain size distribution. So this is a frequency versus grain size. We see there are lots of very small grains, but we see a distribution of much larger grains. This distribution can be evaluated and tested, for instance, in a probability plot, to look at that distribution and see, does it make sense? What's the distribution of that material, the grain size in that material? This quantitative measurement of the grain size distribution, we have to ask ourselves what we define to be a grain. What's the, for instance, the change in orientation that we could use as a grain boundary? Are there systematic biases towards our sampling? I.e., for instance, are we missing very small grains or missing, for instance, very large grains? We have to be careful to consider the edge grains in our problem. We have to consider what is a representative area of our sample and how have we sectioned to obtain that. What is the representative number of grains that's responsible for describing this distribution function? That's important especially towards the fine grain material and the coarse grain samples. What sampling needs to be done? How have we cut the sample and looked across the processing to give a representation of, for instance, an extrusion process? It's also important for us to consider what is that grain size used for? Is it a quality assurance for us to verify that the same grain size has been produced each time? Another aspect is a grain is fundamentally a three-dimensional object. Do we have to worry, for instance, are they sort of elongated ellipsoids? Therefore, the sampling of that grain size distribution will influence how big we think those objects are. But we can start to see the potency of the EBSD technique in this evaluation. We can measure the average grain orientations and we can track how that evolves. In this example, we're looking effectively at, I think it was in situ sort of annealing to enable recrystallization of a magnesium sample. These little plots, we'll discuss them in a lot more detail, but they show effectively the distribution of c-axes in the material, and effectively we can start to see that there is a change in the orientations. We can see effectively there is a nucleation of sort of new grain orientations that's changing the strength of this pole. And that can be very useful in trying to change the anisotropic properties of this system. And so the texture can be, it's very important if there's anisotropic elastic modulus, strength, thermal conductivity, resistivity, a whole range of other bits and pieces. We can also evaluate the interfaces between grains, and we can consider therefore the sort of specialness of different boundary types. In the FCC crystals, there are specific boundary types where you switch from, say, an ABC stacking to a ABC BCA structure. That is the 60-degree or 111 type twin. There's an associated small stacking fault in that system. This is the sort of sigma 3 boundary, special boundary, and they may have special properties with regards to, for instance, stress corrosion cracking. And so we can evaluate the shape and distribution, and also the morphology, so whether they are, say, coherent or incoherent structures in the material. We can go one step further, and if we've got, say, deformation twins that are present, so this is in a zirconium sample, in these deformation twins we can evaluate effectively and segment out the different twins and their parents. And we can evaluate the different types of twin, so in this example it's the difference of T1 and T2 type twins, and of course C1 type twins, so different how they can form and create changes in the crystal lattice. In this example I think it was due to the change in shock in that material. We can also evaluate the relative phase fractions. So if we have two different crystal structures, in this example it's a two-phase titanium alloy where we have a high temperature beta phase that is retained, but as the material cools it grows a low temperature alpha phase. We can look at the relative fraction and morphology of those different phases, and we can also look at the relative orientations between the BCC phase and the HCP phase. Those of you who are familiar with the titanium system know that there is an allotropic phase transformation, where effectively the 110 type crystal plane in the body-centered cubic is typically inherited to give rise to a basal plane in the HCP phase. And there is an inheritance of the 111 crystal direction with the A-type or 11 bar 20 type direction in the HCP. And this is called the Burgers orientation relationship. So we can start to see that the complexity of different phase fractions, their morphologies, and their microstructural relations and the interface types can easily be discerned with EBSD. We could also simultaneously collect things like energy dispersive X-ray spectroscopy to get a chemical signature as well as the crystallographic signature of those phases. Typically in EBSD we'll be doing a phase classification problem where a priori we will have an idea about the phases that are present and we will test what the best fit is. If we're trying to do a phase determination, that requires a significant amount more work and we have to be very careful about the conclusions that we can make. But this is very easy and very powerful for the technique to do this phase classification problem. We can also look at orientation analysis, and so this is a lovely example of looking at some perovskite films that was done in the Netherlands. And in this example, effectively through in situ annealing of this material, we see that we get nucleant grains that will grow out as the material grows, and they're almost like flowers as they grow. And there are specific crystallographic textures associated with those sort of growing of those petals in this material. And this controls the sort of domain structure and perhaps the electronic activity of this perovskite structure. We can look effectively in fracture surfaces. We could look, for instance, at the facets that are formed, so those flat interfaces. So in this example, cross-sectioning focused iron beam machining was done. EBSD was done on the cross-section to reveal that this facet is a sort of prism-type plane in this titanium example. We can look at, I love this example from EBSD of materials in the natural world. So trilobites are sort of critters that will exist in the ocean. Broadly for this story, if the trilobite is located towards the top of the water, it would like to understand the direction of where the light is coming into it, to see where threats, for instance, are existing. If the trilobite exists much lower in the water, it wants to gather as much light as possible. By looking at the mineralization of the lens in the eyes of the trilobites, Torney et al. Evaluate effectively the growth of the calcite crystals as they grow into the material. The calcite crystals as they grow in, and by mapping the c-axis orientation, we can see how the lens is formed. And this shows in this example, effectively, we're bending as much light into the lens as possible, which implies that this trilobite was living much deeper in the water of these systems. We can also use this to understand things like planetary formation and geological crystals. And so this, for instance, shows us by looking at the crystallographic orientations of a badarite structure, we can effectively infer the parent or high temperature zirconium, dioxide structure, a zircon type structure, a zirconia structure, apologies. We can look at that, and that enables us to understand effectively the growth of the zirconia, and specifically this is a particle that records some of the highest temperature experienced at the Earth's crust, associated with the direct impact that's present in these materials. We can also evaluate in engineering alloys. We can evaluate, for instance, precipitates. We can look at their crystal phases and how they're present across the microstructure. Typically, we can look at larger domains or regions than are found in, say, a TEM type analysis. We have this spatial information, which is one up above, say, an X-ray diffraction, powder diffraction analysis. And we can also link this with, say, EDS analysis to look at the chemical variation. We can, of course, go across different techniques, so we can combine EBSD, EDS, with then extracting TEM foils to look at the details of some of those interfaces or chemistries, etc. With this, we're going to stop section 1, and hopefully you'll join me for section 2, where we'll look at how EBSD relates to crystal orientations and some basic crystallography.